Welcome to the discussion on solution for this internal assessment that we had on 9th Jan. So let us look at the first question. Choose the option which gives a resistor value, an actual value of 47K or 47,000 ohms is given, but we need to represent it in an engineering notation form. Now, what is engineering notation, which I have already explained earlier, maybe to recall. So these are the standard prefixes that we have. If it is higher values, we need to mention about kilo, mega, giga, tera, as well as otherwise milli, micro, nano, pico. Now we need to convert whatever value we have, actual value, into any of this form, wherein we can finally make them as milligram or microampere or kilometer, like that. So we need to have this value, we need to make it between 1 and 999. So how will you change this now, which is actually falling under that category? It's very easy. 47 kilo ohms gives you a value which is 47, which is within that range. And then kilo ohms, how do you say? 10 power 3. We need to change it into 47 into 10 power 3. And we should not write it as 10 power 3. We should write it as kilo ohm. So this is the answer. C is the answer for this. Now, let us look at this. Now, if your company is into manufacturing 100 ohm resistors, okay, it's not that your company will manufacture only 100 ohms. Assume that you are manufacturing different resistors and different products, components. But take an example of 100 ohms with a tolerance value of, what is tolerance? First of all, tolerance is you are trying to manufacture some resistance. In our example, it is 100 ohms. But actually, after manufacturing, you will not get the exact 100 ohms, maybe something different. Now, what is that difference will be? It will be something plus delta ohms or maybe minus delta. It could be lower than the value that you have, or it may be higher than the actual value you want to manufacture. Now, it depends on the quality of the manufacturing. If you are doing a very good job of manufacturing the resistance, it will be always the exact value. Otherwise, there will be something more or something less. Now, I'm saying that we are trying to manufacture a tolerance resistor with a tolerance of 5 ohm, 5%. So, whatever I manufacture, it should be falling within the range of plus or minus 5%. Now, what is the 5% of this value? First of all, 5% of 100. I have given the hundreds. We have given hundreds so that you will not be making any mistake, because we said that calculator is not allowed. So we wanted to make it as easy as possible for you. So this is actually 5% of this will be 5. So the variation in the resistance that you can manufacture should be within plus or minus 5 to 100 ohms that you have. That means the value can be 10 plus 5, that means 105 ohms, or it can go down to 95 ohms. But you don't want any resistor which is at 94 ohms to be selected. Okay, it should be rejected. The quality check, QC, you might have seen, quality team should check that and then verify whether any resistors is below 95. You should reject it. But you should also reject if the resistor whatever you manufacture is going above 105, because we have committed that all our resistance will have only 5% of tolerance. If it goes to 106, it means 6% tolerance, which is a higher value. So if your company is into manufacturing 100 ohm resistor with a tolerance of 5%, then your company's quality team should reject all the resistors which are having the resistor values higher than 95 ohms. No, you cannot. If it is 100, will you reject it? Higher than 95 ohms is not the correct option. Lower than 105 ohms? No, that is also, even if you are lucky to have a resistor which is 100 ohms, you should not reject it because it is lower than 105. So that is also not a correct option. Now, what is this? Which are lower than 95 ohms? Okay, any resistor value which are lower than 95 ohms, equal to 95 ohms, so I am fine. But lower than 95 ohms, I should reject it. Or higher than 105. Okay, if it is more than 105 also, we should reject it. So our safe range is this. So the correct option is C. I hope this is clear. Now let us first understand the question. Now we are into third question. In the circuit below, assume initially ABC is given 0, 1, 1. So let me draw this to, sorry about the bad picture. Okay, now let me take it. I have X nor. Oh, sorry. Okay, it's not straight line. Sorry about it. Now just let me draw a straight line now. Okay. Now this is NAND gate. Now assume ABC is initially, what is ABC? This is A, this is B, C. ABC is initially 0, 1, 1. So let us apply those values 0, 1, 1. Now what's the output? XR, different input is 1, and this one is coming here. Then this is same input, so XR will give 0 output, but XNOR it is, so this is 1, and this one is coming here, so it will be 0 here. Then this is 0, this is 1, and this is 1. This AND gate, first consider an AND gate, then all inputs are not 1, so AND gate output will be 0, but it is NAND, so this will be 1. So for a given ABC of 0, 1, 1, ABC of 0, 1, 1, we are getting an output which is 1. Now let us read the question. In the circuit below, initial value was ABC 0, 1, 1. Choose the correct value of ABC, which will make the output X. Now X is equal to 1. For ABC of 1, X is equal to 1. Right? For ABC of 0, 1, 1. Now choose the correct option, which will make the output X to become complement of its initial value. What was the initial input given? ABC 0, 1, 1. So the X will be initially, it will be 1. Now I need to give some other different ABC which will make this output to become 0 now. So I have to choose something which will make the output equal to 0. So let us now see how do I do it. Okay. Now we need X to be a value which is 0, which is complement of the original value. Now which input, if I give, will it satisfy that? Now first thing what we should do is, if it needs to be 0, you have to now backtrack it. Now NAND gate output has to be 0. That means this AND gate should give me 1. Then if it needs to be 1, all the input should be 1. Okay, all the input should be 1. No, this all should be 1 for me to get the output of AND gate as 1, and the NOT of that will be 0. So that's what we want, X to be 0, because originally it was 1. Now what should be the C value? Now backtrack it. It should be 1. In that case, this should be 0. Now look at this. ABC is the thing. So A is here, B, C. So that's the same sequence you should assume. Now, which value of ABC, whether 100 will give me or 110 will give me. Okay, let me make 0 bigger, or 101. Now we found out that C needs to be 0. If it is output has to be 0, AND gate has to give me 1, and if AND gate has to be 1, I should make sure that at least first C should, not of C should be 1. That means C should be 0, because if I get a 0 here only, I will get 1 here, so that the other two inputs can influence. But if this itself is 0, nothing can be done. So we need to make sure that C is 0. Now, out of these two input, this is gone now. Now we need to choose between these two, which will be the right answer. Now let us trace back. Now this needs to be 1, of course. That means this we saw that old value we should not consider now, because this is old value is earlier 1 and this is 0 now. So we should backtrack now. I want this to be 1 now. Okay, this input. If this needs to be 1, before the NOT gate, it should be 0. In that case, XR should give me a value which is 0. In that case, we know that one input is 0. When will the XR give me a 0? Only when this is also 0. Okay. If it is a 1, it is going to give me a 1 and a NOT of that will be 0. So I will not get what I want. So B has to be 0 now. So we are now closely going to this. Okay. Please remember, we have come to this now. Now we know that B cannot be 1, because B has to be 0 here for this XR to give me a 0, and then a complement of that needs to be 1, so that we'll see that all of them becoming 1, and we'll get the value here. So B is ruled out. Now still you cannot choose A as an option, because I have given none of the given option is correct. So maybe this A being 1 may also be wrong. So we need to verify it. Now we know that this has to be 1. This needs to be 1. In that case, we know now B is 0. Then when will the XR output will be 1? Only when I have A as 1. If I have it as a 0, then XR will be 0. So output. So A has to be 1. Yes, we got the answer. So this is the correct answer, because if I give ABC as 100, then we will get the complement of earlier output. Okay, so this is the correct answer. So option is 100, which is A. I hope this is clear now. Question number 4. In the circuit below, due to a circuit fault, the point P is always 1. Then the output F will be. Now F is given in terms of the inputs. A, B here, C is there. So we need to find out what will be the output if I have this P, the point P here happens to be always 1. That means what should we do? Now we have a circuit here which is taking the input and then feeding it here. Okay, the same input is coming, all that is fine. Now if you want to actually solve it as early as possible, okay, or with the minimum effort, what you should do is you should trace this, because we know this input is 1. It doesn't matter what is here, because A and C is A and C do not have influence on the output here, because this is going to be always 1. The point P is always going to be 1 because of some circuit fault. That means it's disconnected, and then directly power is coming and it is giving a 1. Now let us trace back, towards the output, not trace back, we will follow it. Now when it is input is 1, this AND gate, the two input AND gate is going to be 1 1. So AND gate's output will be 1, but it is a not, it's an AND gate. So this is going to be 0. The output of this gate is going to be 0. In that case, whatever may be the input coming from here, this is 0 here. Then this AND gate is always going to give me a 0 output, because one of the input is 0 because of this becoming a 1. So this 0 is going to influence the output. AND gate's output is 0, but NAND it is. So this output will be 1. Now, if this is 1, whatever is the value of B is going to be coming out here. So this is 1. So AND gate will be B. Because it is NAND, it is B bar. Again, we are doing a inversion. Okay, this is NAND gate with both the inputs shorted, is a NOT gate. So you got a B bar here, but again we are inverting it, complementing it, so you will get a B. So F is equal to B is the correct answer, and it happens to be option B. So option B is the correct answer. I'm not drawing the picture here. It's a very complex, but I hope my cursor is visible on the screen. In that case, maybe I will, I'm not sure whether the cursor will be seen. So let me see, P is equal to 1 here. Then this NAND gate is going to, this will be 1. I'm talking about one NAND gate after the P. This will be 0. Then it is going to another NAND gate. This is 0. So the AND gate output will be 0. Not of that will be 1 always, irrespective of whatever is the input here. This is a don't care. Okay. Don't care, because whatever may be the value 0 or 1, this decides the output. So if this happens to be 0 because of this fault, we have output which is 1 here. Okay. Now this is feeding into our circuit, which is a NAND gate with a B here. Now this happens to be 1. Then whatever is the value of B, whether it is 0, the AND output will be 0. If it is 1, then it will be 1. So because this is always 1, whatever B comes in, it will come out. Now since this is a NAND gate, you will get a B bar here, a complement of B. Again we are having a NAND gate which is nothing but a NOT gate. So this will be B. So F is equal to B. Okay, I hope if the cursor was not visible in my recording, I have drawn this for clarity. Okay, I hope this is clear now. Okay, I have shown the result already. Now, in which of the following base system 711 is not a valid number? 771 is not a valid number. So you need to choose if base 8 is it a valid number. In base 8, what are the symbols you have? 0 to 7, because 8 unique symbols are there. So we have 771. So octal is correct. This number is correct. Base 10. Base 10 is, you cannot say it's wrong. 771 is a correct value. So base 10 also, decimal system, is correct. What about base 16? Base 16 is much more than this. Okay, we go up to 0 to F. So 771 is correct in base 16 also. So none of them happens to be invalid. Now none of the above is a correct option. So D is a correct option for question number, I don't know what the number it is, 5. Okay. Now what is this? Question number 6. Choose the correct statement about the three numbers given below. 1, 1 in 10, which is nothing but 11. 1, 0, 1, 1 in binary this system. So please do not find a 2's complement here. I never said that it is a 2's complement. So you need to treat this as an unsigned number. Okay. So in that case, it will be 8 plus 0 plus 2 plus 1, which is again 11. Okay. And then 1, 3 octal. 1, 3 octal is nothing but 1 into 8 power 1 plus 3 into 8 power 0. This is 8 plus 3 equal to again 11. Okay, I am writing 11 because you may again confuse with the binary number 1, 1, which happens to be 3. But now all of them are 11, okay, in different forms. So all of them represent different values is wrong. 2 of them represent the same value and the other is different, which is wrong. All of them represent the same value, which is the correct answer. So A is the right option. Okay. Now, I think I don't need to worry about showing the answer. Now, how do we know whether it is high pass filter? Okay, let me explain it. So, we are changing the frequency. Okay, frequency is changed. And what will happen to the role of, what is the role of capacitor here? See, in a typical DC circuit, okay, well, let us to understand this, let us use a digital circuit. Okay, Now I have some voltage here appearing and some resistor is there, and this is the R out. Okay, this is the output. Whatever voltage coming across this resistor is the output what I am getting. Now this is some resistance which is there in the middle. Now this is the input I am giving. Output I am getting it across R out, this resistor. Okay, whatever is the R here, V out we are getting. So this is a resistor R out I am calling, and I am getting a voltage which is at this point. Now suppose if I have a V and then some current will flow. Now when will I get the maximum output here at this point? Only when the voltage drop across this resistor is small. Okay, it's delta, and the maximum is appearing here. Suppose if I am giving 10 volts and this is only some zero point 0.2 volt is drop across this, and the rest of the 9.8 volts is coming here, then we are getting a maximum output. In that case, what we want this resistance to be as small as possible, as small, okay, as small as possible for us to see the maximum part of the input voltage at the output. Otherwise, the balance will be dropped across this resistor. So, if you apply the same logic here, then we want this to be even this XC, which is a reactance of capacitance or the AC resistance of capacitance, needs to be when it is small. Suppose if the resistance is small, then we will get max output, right? Max out, because in the same whatever we see it in the digital DC circuit, the same thing is true in AC. Only thing is here frequency is changing and the resistance across the capacitance is going to be changing based on the frequency. So when I increase the frequency, suppose, what will be the reactance? Now reactance across the capacitor, I have given you the equation there, omega C, which is nothing but 1 by 2 pi f into C. So the frequency component is below. So if I increase the frequency, I am going to get this XC value going down. Now, if XC goes down, the voltage across this will be small and the maximum drop will be coming across the output resistor, right? So, if my input is of higher frequency, the frequency value is high, then XC is going to be small, then the voltage across this will be small, some delta, and the maximum output will come here. So this is the output. That means at higher frequency, I will get maximum output. But when I am giving a low frequency, suppose the frequency is low, then the resistance value will be high because it's a inverse ratio. Okay, frequency is below and XC is inversely proportional to frequency. So at lower frequencies, XC is going to be high and maximum drop will happen here, maybe big delta, then my output will be small. So lower frequencies will not be seen at the output, higher frequency will be seen at the output. That means what? This is the high pass filter. Okay. I hope even if you are not understood in the class, in our explanation, this makes it clear to you. Okay. So you need to give both this reason as well as HPF. Okay, if you are given only high pass filter, but if your explanation is wrong, then you will get only 0.5 for it. Okay, the minimum resolution in a marking system will be 0.5. We will not go below 0.25, 0.1, 0.5 and all that. So if you are given only HPF, then 0.5 you will get. Explanation is also correct, another 0.5, so 1 mark. Of course, if you don't mention this, you give any other filter, then it's going to be 0. Okay, now let us go down. I'm worried that you will see the answer. Okay, question 8. Now I have given you some, we have put some component and all that, but don't worry about it. We will just see, this is, see whether I draw a current like this or I show current like this, both are same. Okay, that's a convention. Either you show the arrow outside this wire, or on the wire, both are the same current. This current is same. Okay, so I2 is coming in. Okay, and then don't bother about the resistor. I1 is going out, and then don't bother about the voltage source, because I am showing you the current, then we can see that I4 is going out, then some I3 is coming. Now what we need to do, put all the incoming current equal to outgoing current. So let me say I2 plus I3 all incoming, and I1, sorry, yeah, I1 plus I4 is going out. So incoming current is equal to outgoing current. Okay, at this point, this is KCL. Okay, now what are the values? Substitute the values now. What are the values given? Okay, 3 is given. I'm not writing ampere here right now. I2 is 3. I3 is minus 5. Okay, equal to I1 is to be found. So we'll let us write I1, and then I4 is minus 1. So minus 1. Now we need to find I1. So plus 1 will come here. 3 minus 5 plus 1, that means minus 1. I1 is minus 1. And please mention ampere now. Okay, this is the answer. I1 equal to minus 1. Now, actually speaking, if ampere is missing, if you are given just minus 1, you should be getting zero point 0.5 marks less. But since this is the first examination in this, so they will give you mark even if you have written I1 is equal to minus 1, which is wrong. You should say whether it is ampere or voltage or whatever. Both of you, all that will get. Okay, but if you are written plus 1 or other values, you will not get the marks for it. Okay. Now, there is a big confusion about these values. So let us now understand it better now. Okay. This is question number 9. Okay. Now let me take some more space here. Question number 9. We have only one number, 1010, and it is binary. The decimal value is represented by the binary number if it is considered to be an unsigned or a signed number R. Okay. Now, what is that I mean? We mean here, if you consider values like this, a 4-bit number. So in unsigned syntax, this is 0 and this is 15. When you treat this as this set of numbers as unsigned numbers, we don't associate a sign bit here. Okay, we don't consider to be a negative number. We don't have any negative number at all in unsigned representation. So this MSB being 1 and calling it as a negative number is not valid. So in the unsigned, if you are considering the pattern as unsigned numbers, we will treat it as 0 to 15. Okay, that means what? This you will compute it as 2 power 3 plus 2 power 2 plus 2 power 1 plus, of course, 2 power 0, which is 1. So this is 8 plus 4 plus 2 plus 1, 12 plus 14 plus 15, 1. Okay, so this is the value if it happens to be 1111. So if I give you this number and we treat it as an unsigned, then what should we do? We should give you should not find a 2's complement here, because we are going to treat it as a positive number. So it's 2 power 3, which is 8. And then this is 2. So it is 10. As unsigned, this value is 10. But now if I treat it as a signed number, okay, how do you look at this number in a different way? So if it is a signed number, okay, I'm going to assume it as a signed number, then 10102. So let me take more space here. Then if we need to find the actual value of this, we need to find a 2's complement, because this MSB is 1. Okay, I'm having a 4-bit number. So this MSB is 1, most significant bit is 1. So it's a negative number. If I want to know what is the actual decimal equivalence of this, I need to find 2's complement. Now, how do you find the 2's complement of 1010? You find the complement plus 1. So this is 0, carry 1. So this is 1, carry 0. So 1. And then there is nothing coming out, 0. So 0. So now find the, what is the value? This is nothing but a 3. So this same pattern 1010, if it is treated as a sign number, its value is going to be minus 3. Okay. So, oh, sorry. I'm very sorry. This is 4 and 2, so 6. Okay. So this is, it's not 1 1. I forgot this 0 here. So it is going to be 4 plus 2, 6. So it is a minus 6. Okay. This is going to be minus 6. So 10 is the unsigned decimal value and minus 6 is a signed number, and which satisfy that unsigned and signed number are. So 10 and minus 6. Okay. It's not 6 and minus 10 or 10 and minus 2. It is 10 and minus 6. That's the C is the right option. I hope you understood this. Again, I will explain. When I treat a pattern, a 4-bit pattern, in this case, if I treat it as a signed number, we need to consider this to be a signed number, and then because it is 1, it's a negative number, so you have to find the 2's complement of it, and then whatever magnitude you get, this is 6 here, you need to put minus here and then say minus 6. Okay. So in fact, you can go from 6 to this number also. If you find the 2's complement of this value, suppose if you are asked to find a 2's complement of 6 or the minus 6, if you want to represent, what do? You find the 2's complement. So go back from here. Suppose you are given a number 6 and then you are asked to find out the signed representation of this number. What do? You find the 2's complement. So 1 0 0 1 plus 1. Then it will be 0 1. Okay. There will be a carry. So that one will come here and there is no carry here. So 0 and 1. So this is the signed 2's complement representation of minus 6. Okay. So you can go from positive number, the magnitude, to negative representation, and you can also find the 2's complement, you will get the magnitude. So both way it is 2's complement. Either to go from given a value, how to find the negative of that, you need to find the 2's complement, and the reverse is also true. Given a 2's complement number, you want to know the magnitude, you need to find the 2's complement. So that's the operation. Now, if you do not know what are the negative numbers, if it is 4-bit number, and I am saying that these are all signed numbers, so let us look at all the combinations, and this will be later on used also. Okay. I'm slightly shifting. Let me come back. Okay, it goes on. Now let me come up to this point. Okay, and then this will continue. Now in signed representation, MSB is 1, then it's a negative number. So negative numbers are starting from here to here. Okay, these are all positive numbers. Okay. Now, how many numbers are there? 4, another 4. Okay. See, these 8 combinations, okay, are 8 combinations are positive numbers because MSB is 0. So what are those values? 0, 1, 2, up to 7. Now, what about this 100? This number, this is very tricky. Before I find the what is the negative representation of this, let us try to find this value. Now all 1 represent what number? Okay, but we know that it's a negative number, but we don't know what exactly, negative of something, right? Minus 25 or minus 30 or what it is. What we should do, we should find 2's complement of this. So if I try to find the 2's complement of this 111, so find the complement all bits, then add 1. So 0001. That means what? This pattern represents -1. Okay, this is -1. So we started off from 0 and then we came up to 7, and then I am saying the combination, this combination happens to be -1. Now what about this? Okay, we in between there are some minus values are there, but -1 is, as the this pattern gives you -1, and we should find out what is this 100 combination gives you, right? So let us do that. So 100 combination, this pattern is negative number, I know, but I don't know what is the value. So what should I do? I need to find the 2's complement of this number. When we do the 2's complement, whatever value I get, that's the magnitude. Okay, so you need to find the complement of this 0 1 1 1, because all the bits are complemented. I need to add a 1 now. Now if I add a 1, so let me maybe write it like this. Okay, I am adding 1 here. So this is 0, we'll get a carry, then 1 plus 1, right, is 0 again. I get a carry, which is 1. So 1 plus 1 is 0. So 1 plus 1 is 0 because we know that it is 2. Now, if you want to represent the 2, you need to take that 1 to here, because we cannot have anything more than a 0 or 1 here. So this value is basically a 2 in binary representation. That's why the carry is 1 when you are adding 1 and 1. Okay, I'm sure you will know that. So this is also 0, 1 plus 1, again one carry will come, and that is getting added with the zeros. So this is the value. Now you should compute this as a magnitude. So it is 2 power 3 plus all zeros. So it is 8. So this representation 100 gives you -8. Okay. Now what are the other values you have? In this pattern 1002 all 111. What are the other patterns you have? We said this is -8. All 1 1 is -1. How many are there? We already saw 0 to this 0 1 1. 8 values were there. Now other 8 combinations are here. Now you know that it is going from -1 to -8. It will be -2, -3, -4, -5, -6, -7, and -8. Now suppose I want to know what is the pattern of -4. I said I have to find the 2's complement of 4. So what is the representation of 4? Let me write here 0 1 0 0. Now if I have to find what is it in negative 2's complement form to represent -4, I need to find the 2's complement of 4. So it is 1 0 1 1. All bits are complemented, and then I need to add 1. So let me add now 0, 1 is coming here, 0, carry 1 is coming, but it is getting added to zeros, so 1. So there is no carry coming here. Okay, it is 0 carry. When I say no carry means it's actually 0 is coming. Carry will always come. Okay, either 0 or 1. So this will be 1. So pattern is 1 1 0. So this pattern is 1 1 0 0. So you can see that I leave it as an exercise for you to find the values of this missing pattern. You will get the remaining 2's complement. So if you have a 4-bit pattern, and then I am calling it as a signed numbers, they are all signed numbers. I'm going to look at this pattern as a signed number. Then whatever values are there with the MSB as 0, I will take it as it is. It's a positive number. Then if I have any pattern which is having the MSB as 1, I will not read it as it is. I will do the 2's complement of it to find out the actual value. So I will get one of these values as actual negative numbers represented in 2's complement. I hope this is clear to you now. In case if you have missed or not understood earlier. So the correct answer is 10 and minus 6, which is option C. Now let us look at the last question of part A. We'll stop with this, solving this, and then in the next recording, I will take up part B. Now, question 10 of part A. Before I start, let us tell you and recall whatever about the parity. This is a parity bit. There is always one bit which is for parity. Data could be any number. Now, in our case, it's a 8-bit number. So, 0, 1, 1, 1 and 1, 0, 1, 0 is a data portion. And there is a parity bit also identified, which happens to be 1 here. Okay. Now, what is so told? You are receiving an 8-bit data along with a parity bit. This is the receiver. Okay. Somebody has sent it. Okay. TX is somewhere here and I am the receiver. I received this bit pattern. Okay. This is the channel, communication channel. Now, what is the purpose of this parity as such? Let me expand it. Now, what is the purpose of this? Suppose someone is sending pattern. So the sender knows what data that person is sending, but receiver does not know. So when it is received, the receiver will know what is the data portion and what is the parity portion. That much they know, whether 8-bit data or 10-bit data, whatever, and then a parity bit, which is applied on this data, and we got the parity bit. Now, the sender is free to choose even parity or odd parity. Now, what does it mean? Based on the data, okay, I can generate a parity bit, but I do it based on either I decide to follow even parity or odd parity. Now, what I mean by even parity? Suppose if I have the same data, x111 and 1010, if I decide that I am going to generate a even parity, I need to choose a bit for it. Okay, let me call it as P even. I need to choose a bit, whether it is a 1 or a 0 or value, I need to choose. How do I choose it? Along with the parity bit and the data bits, I need to make sure that I have even number of ones. Even number of ones. Now, this data is having 1, 2, 3, 4, 5. 5 ones are there. But if I choose to follow a even parity system, then I need to make sure that along with the data and the parity bit value, I need to have even number of ones, because sender can always decide that, because it knows the correct data value it has and number of ones in the data, and then you can generate the even parity or odd parity. The value for the parity bit you can choose based on what they decide to do. Along with the parity bit, I should make it as a pattern should have number of ones as even. Then if I am following even parity, for this data which is having 5 ones in it, I need to make a PS1 so that we, along with this parity bit and the data bit, it will be even number of ones. 1, 2, 3, 4, 5, 6. 6 number of ones. Please remember, we are not going to change the data value for satisfying our condition, because data you are not supposed to touch. The transmitter should not touch the data, but it has a freedom to choose the parity value. So based on the number of ones in the data portion, it can choose the parity. But suppose transmitter decided that, okay, I don't like even parity, but I want to do odd parity. Then the P bit should be 0, because already the odd number of ones are there in the data portion. So I should not put one more one, which will make it even. So, right? So number of ones should be 0, odd, including the parity bit. So I should put a P odd. Parity, if it is followed is odd, then I should put a 0 there. Now what is happening is, when I am sending this data to the receiver is already told whether the transmitter is following even parity or odd parity. That is known to the receiver. Now what does the receiver do? It looks at the number of ones in the received data. Now suppose the sender has told that I am going to follow even, then it will look at the content it has received. It will count again 1, 2, 3, 4, 5, 6. So six ones are there, which is even number, and the sender said that I am following a even parity, so the data is received correctly. So it will correct, it will not reject the data. But if the sender has said that is even parity, and then one of the bit has become, instead of 1 it has become 0, or 0 has become 1. Now what will happen is, now assume that this has become 0, then and it is following even parity, it knows already, but the received data is 0 here, one of them has become 0, then number of ones will be odd now. Then the receiver will know that yes, I received the data wrongly, because I know that the sender is following even parity, but now I am getting a number of ones in the data along with the parity as odd, so some data corruption has happened. But remember, the receiver will not know whether which bit is corrected, which bit has been corrupted, or whether the parity bit is corrupted or the data bit is corrupted, but it knows that some error has happened. So it can detect some one bit error. But what if two bits have changed? Suppose if two ones have become 0, then number of ones will still remain as valid. Okay, if suppose if we have 6 ones normally in this data now, suppose two of them have become 0, there's a 2-bit error, then still the number of ones will be even. Then the receiver will assume that yeah, this data is correct. It doesn't know the actual data, right, a priori, so it will think that even number of ones are there is good. So in this parity system, more than one bit error will not be detected. Okay, so more than one bit error will not be detected, and it cannot correct the bit. It will not know that one bit error also, it will not know which bit is corrupted, but it will know that some error has happened. So it has to ask the sender to send the data again. So that's the only option. So two-bit error, it will assume that everything is fine and it will take it. So I hope this is clear now. Now let us come to the question. Okay. You are receiving 8-bit data, which is shown here. Assume that there is a 1-bit error either in the data or in the parity bit. Okay. I am saying that the data what is received, what is shown to you, has already corrupted. Okay. It's not actual data what the sender has sent. Okay. Remember, whatever data is seen here is corrupted, because I'm saying that 1-bit error has happened. I'm not saying which bit is. Okay, I don't know whether 0 has become 1 or 1 has become 0. We don't care. But this is what the receiver has received. But I am saying that 1-bit error, I am like a god, I know that 1-bit error has happened. Assume that there is a 1-bit error either in the data or a parity bit. If the value received is shown below, what was the parity being followed by the sender? Now imagine, I'm saying it's 1-bit error only, and what is the value that I am getting is this, then what was the parity followed by the sender? That means what? While the sender sent the data, one of the bit would have been 1, or one of the bit, one instead of 1, it would have been 0. Let us, for a convenience sake, let us assume that if you are, somehow you have some knowledge that that 1-bit error happens to be this. Okay, you assumed. Okay, this is what sender would have sent it, but this error has happened and it has become 0. Now count the number of ones. 1, 2, 3, 4, 5, 6, 7. So the sender is sending 7 ones. Okay, either 0 has become 1 or 1 has become 0. It is true. So sender is sending actually odd number of ones, but it has been received as a even number of ones because 1-bit error has happened. That means the sender TX guy has followed odd parity. Okay, so you cannot say both even and odd parity. None of the above is also not valid. So option B is the right answer. Okay, I hope if you are not understood parity, it is clear now. I'm not going to explain it even in the revision, because I think this is a good place to explain about the complete thing. So I will stop here because the recording has already crossed more number of hours, where minutes, which will not get your attention. And part B will be solved in the next video later on, and it's already for me beyond 12 noon, 12 midnight. So I'm stopping now, and see you maybe later with next recording. Bye bye. Have a nice day and good night.